to make sure you guys are all in the right place. So just to introduce some things, again, we only have 2 hours, so I'm going to try to get some things out of the way here so far. So, all right, so these are important things that you really should memorize before you get into the exam. I don't have enough time to cover them really in depth, but I promise you they're not concepts that are too difficult. It's just sheer memorization. Can you memorize a chart? Can you memorize how the rules to naming things, right? If we have time, I'll introduce some examples about these topics, but I'm just letting you know here forefront, we might not get to these things, but these things are still all equally important as the things we will cover. So also, if you guys ever want to come back, like, oh, you missed some notes or anything, this is being live streamed to YouTube. So if you YouTube UCF Study Union 2018 Chem 1, this will all be recorded on a video for you guys to revisit. Okay? So, any questions about that? All right. So, let's start off like with the beginning. So we're going to go off chapter 1 here. So, if I ever start writing off the doc cam, if someone could please let me know, that would be really appreciated. Okay. So, I'm just going to show you guys this. So this is the basic agenda for what we're going to do, what I'm going to try to hit. So we're going to start with unit conversions, going into basic stoichiometry, leading into solution stoichiometry, gases, thermodynamics, and then we're going to end with the quantum, which is just the drawings and stuff like that. So, there we go. All right, so let us start with unit conversion, right? Okay, so unit conversion is pretty much the cornerstone of chemistry. If there's anything you learn from this session, I hope it's how to convert units properly, because everything you do in chemistry, as you've learned through this past semester, is doing conversion ratios, converting moles into grams, grams into moles, moles into parts or atoms. So it's very important that you guys understand effectively and efficiently how to convert units. So it's all about setting up a ratio, right? So what you want to do is you want to, so the first thing is start with what you have. So that's step 1. So in this problem, we are asked to calculate the mass in grams of 1.22 times 10 to the 27 magnesium atoms, right? So like the first step is, we start with what we have. We know we're in parts or atoms. That's the unit. So that's the unit we're going to write first. Atoms of magnesium, right? Then we're going to input the number we have. So we have 1.22 times 10 to the 27. So next, we need to create a ratio that's going to bring us to what we want. So in this question, we want the answer in grams. So we need to create a conversion or a fraction that will cancel out what we have and convert it into what we need. So if you guys are aware, is there a way to convert straight from atoms into grams? No, right? We have to convert it into moles first. So we're going to set up that ratio. So does anybody know when you want to cancel something out, what side does it go on, the top or the bottom? Yeah, in this case it would be the bottom. Just for reference, generally it's not specifically the bottom. It has to be on the opposite side of what your unit is on. So here, atoms is on the top, so we're going to put atoms on the bottom. So we put the atoms on bottom. And who knows how many parts or atoms are in 1 mole of any substance? Okay, yeah, exactly. Avogadro's number. So 6.022 times 10 to the 23rd. And that's what we want, 1 mole of Mg. Now we continue the ratio, so now we know we're at this next step, and we still want it in grams. But now we have that conversion factor, so now we can go from moles to grams, and we know that would be 1 mole on the bottom, to grams of magnesium. How do you find the grams? Exactly, periodic table. You use the atomic mass. I already have it written down. The atomic mass is 34.3 grams of Mg. And so then you just multiply across. Can someone do that calculation for me? Yeah, if you have a calculator. Is it? Yeah, it's 24.3. Good catch. Yeah, sorry, my handwriting gets a little sloppy sometimes. Okay. So while you guys calculate that, I'm going to write the next problem, okay? So the next unit conversion is simply 4.03 moles of carbon dioxide, and we want that in grams. So did you guys get the answer for the grams of magnesium yet? Okay. Okay. Okay, so for moles, how can we go from moles to grams? We did it in the last problem, so exactly. You just do the mass over mole, and that's this unit conversion right over here. So we can just do 1 mole of CO2 over the 48 grams of CO2. And so you should just get 4.03 times 193.44 grams of CO2 here. So any questions on unit conversion, how that goes? Okay. Now this brings a good question about sig figs. How do you guys feel about sig figs? Maybe a little. All right, so again, sig figs are another rule that is one part of the naming conventions and things we want to learn. But I'm going to give you a blind tip. This works about 8, I would say 7 to 8 out of 10 times. Like let's say you're on the final and you forget, like, uh-oh, I don't know what my sig figs are. I can't remember how the sig figs are for adding or subtracting. If you have to guess, go with 3 sig figs. That's my tip from me to you. It's not very professional, it's not very official, so it's not guaranteed to work, but just from my experience, most of the time it's 3 sig figs. So that's just a tip, all right? All right, so now that's basic unit conversion out of the way. So now we can start going into actual like stoichiometry, right? And so stoichiometry is basically just the idea of finding different things about chemical reactions and using what we know to solve for different ones. So in this case, we have to solve for a reaction where a hydrogen-filled balloon is ignited and it reacts with oxygens, right? Okay, right? And so we're given that there was 3.7 grams of hydrogen and 17.3 grams of oxygen. And so we're asked how many moles of water vapor is formed? So the first step here that we have to do is we have to have a balanced reaction, right? We need to have a good idea of the surroundings and what exactly is happening in this reaction. So we know that the balloon is ignited, right? So it has hydrogen and oxygen, right? And so you know that hydrogen and oxygen are both diatomic when they are in gas form. So we know it has to be H2 plus O2, not them by themselves, because they can't just be by themselves as a gas. They have to be together. And that will form H2O as a gas. Now, is that reaction balanced? No, right? So we have to balance it. Otherwise, we're going to get a wrong answer. So we have 2 oxygens, but 1 oxygen on this side, 2 hydrogens, 2 hydrogens. Well, we have to balance the O's, so we're going to put a 2 out in front here. So now we have 2 oxygens, 2 oxygens, but now we have 4 hydrogens. So we just make this 2. So now we have our balanced equation. So then following that, it's just unit conversion. Now that we know our ratios, we can just convert units to find our answer. So we start with what we have, right? So we know we have 3.7 grams of hydrogen, H2, and we want to convert that into moles of water vapor. So first, we have to convert hydrogen into moles of itself, because we can't compare mole ratios unless both of the units are in moles. Okay? So we're just going to do the mole ratio. 1 mole H2 is approximately 2 grams of hydrogen 2. Then, from there, we need to convert from moles of hydrogen to moles of water, or H2O. But we have the balanced reaction for that. We know that 2H2O makes, or 2H2 makes 2H2O. So we know we have 2 moles of H2, and that will go into 2 moles of H2O. This will give us our answer in moles of H2O, which is what we're asked. And so essentially we just plug that into the calculator. 3.7 divided by 2, and then 2 divided by 2 is 1, so you just multiply that by 1, and you're going to get 6.845 6.845 moles of H2O. Now the second part will ask you, now that you have moles of H2O, or water vapor, how many grams is that? Again, just another simple unit conversion that we can work out. Start with what we have, 6.845. We create our mole ratio. Moles on the bottom, we want to cancel that out. And we have, and then the grams on the top, and H2O is about 18 grams. And so you're left with 123 grams of H2O. So any questions on that? Anybody get lost? Or are we all good? I know it's Sunday, but you guys are really quiet. Given, I know doing chemistry on a Sunday isn't the most exciting thing, but you guys are almost done. Push through. Come on. Right? All right. So continuing on, right? So now that we know unit conversion and we have our basic ideas of stoichiometry, now we have the more questioning things that are formula-based, right? So very often you're going to be asked about isotopes and their mass abundance, the atomic mass of a compound or an element. And so it's very important that you guys understand how to solve for mass abundance and understand the relationship between isotopes, the atomic mass. Oh, good call. All right. Okay. And so Mass abundance is just this idea that there's a limited amount of isotopes and elements within the world. So we can devise a formula that can calculate, depending on how much percentage of this isotope is present, we can calculate the actual average atomic mass of an element. And so the formula for that looks something like this. All right? You have the mass of your first isotope, and you multiply that by its abundance, or its percentage. All right? And then you're going to add that onto the mass of the second isotope times its percent abundance, and etc. Depending on how many isotopes, you can keep going on forever. It just follows the same trend. M1, %1, M2, %2, and so on. And that formula will be equal to the atomic mass of the compound. Right? And so remember that these are percentages, right? Because sometimes they like to get tricky, especially on the ACS, where they'll give you a situation where they'll give you the isotopes, but they'll only give you some of the percentages or the abundances. But don't fret, just because they don't give it to you, you got to remember, what is one thing we know about percentages? They add up to 100. So you can always subtract out to solve for the missing abundance. Remember that, okay? And so our question is, if we're given that copper has 2 naturally occurring isotopes labeled Cu63, which has an atomic mass of 62.9396 grams per mole and a 69.17% abundance, while its other isotope, Cu65, has a mass of 64.9278, an abundance of 30.83%. Calculate the mass of Cu, right? Or copper. And so in this case, we're just going to follow the formula, plug and chug, right? So we know the mass of Cu63 is 62.9396 times its percentage. Now here's where you got to remember and be careful. Percentages in numbers, when you plug them into your calculator, they're fractions, right? So you have to put the decimal. You cannot put it in as the percentage, because if you do, you're going to get a number that is much higher than the actual expected answer. So for Cu63, the percentage is 69.17, which is going to break down to 0.6917. Not, you don't plug in 69.17. That will give you a wrong answer. Okay? And so we follow the same trend here, where Cu65 has a mass of 64.9278, multiplied by its abundance, 3083. You multiply that across, and you add it up, and you should get 62.23 grams per mole as the mass. Now, sometimes they might give you an element, but most likely they'll label it as element X or something like that. And the reason they do that is because you could do all of this math, or you could just check your periodic table and it'll give you the answer, right? So don't expect it to be this easy. A lot of the times they're going to label the element as a mystery element, so you do need to know that formula. Okay? All right. Okay, so now that we've gotten the base, what's up? 62.23, yeah. Right? So now that we have the precepts and the basics of chemistry now we're going to get into the more complicated stuff. This is where the math gets a little more intensive and a little more applicable to concepts, right? And this is solution stoichiometry. So this is the idea of when we have multiple parts moving instead of just a one-way reaction like combustion or stuff like that. So let's just, before we jump into solution stoichiometry, let's try to get our types of reactions down, right? So, sorry. Okay. So these are the important reactions that you need to know for Chem 1, right? So we have our basic reaction, which is combustion. And the reason I'm telling you guys this is because sometimes they won't even give you an explanation or a balanced equation. They're just going to tell you the type of reaction, and you need to know what that entails. So if I say combustion reaction, you should know that oxygen, O2, is a reactant, while carbon dioxide is a product. That's for all combustion reactions. And you should be able to balance it just off of the fact if I give you something like magnesium is burning, you should know that's a combustion reaction involving the reactants of O2 and magnesium, and it results in CO2 plus another form of magnesium. Then we have redox reactions, which we're going to go into more with the solution, where nothing is fundamentally changing except the oxidation states of the elements themselves, which just means we're changing the charges. We're manipulating whether it's a +2, a +1, -1, -2. We're just manipulating electronic charges, and that's really important for solutions because depending on their charge will also dictate the type of bonds they make, whether they dissolve or whether they form precipitates. Then we have precipitation reaction, again, which is leading in from redox, is a reaction where a precipitate is formed, where the solubility rules are broken and you're going to form a precipitate because it isn't soluble in water. Then you have acid-base, which is pretty self-explanatory. It's a reaction where an acid and a base react with each other and they neutralize each other. Or in one case, an acid may be stronger or a base may be stronger, depending on which will affect the pH respectively. Okay. So fundamental to these ideas, right, is you need to know mass percentages and you need to know how to calculate them, right? So if I say calculate the mass percent of carbon and C2H5Cl, you need to be able to do that, right? You need to be able to tell me this compound is made up of this percentage of a carbon, and for that we can do different mole ratios, which you'll find out will affect later in gases, right? So again, we have to, if we're dealing with a mass percent, innately we should have the mass of a part divided by the total mass. That's how percentages work. So if we're trying to find the part in this compound, which in this case is carbon, we want the mass of carbon. So we know there's 2 carbons, or 2 moles of carbon in this case, and we can say that we can calculate how much that weighs, right? Periodic table. We know carbon weighs 14 grams, is it? Or 12? 12. 12 grams. And you simply multiply that by how much is present, the 2. So we now know there's 24 grams of carbon. So we now know the mass of the part. And now, so the total mass should be everything added together. The 24 grams of carbon, H5, and H is about 1 gram, so the 5 grams of hydrogen, and then Cl. And Cl is about 35.45 grams. And then that 35.45 grams of Cl. You add that all together, and you get 61.488 grams. And so now that we have the mass of the part, we have the mass of the whole, we just divide them. Right? 24 grams divided by 61.488 grams. That should just give you 0.39. Don't forget, it's asking for a percentage, so you have to make that a percent. Just simply multiply by 100. You get 39.1%. What's up? Again, for this case, I just go with 3 sig figs. But depending on the numbers, like right here, we have 2, 1, 2, that's multiplied. So technically it should be 1 sig fig, but just going off of the number, I'm just doing 3. So if you shouldn't round, because here it's not the best example of work, because again, limited time, so I'm trying to push through. But never round until your final answer. So technically, this shouldn't be 12. This should be like 12.022, right? And then you go off of the one with the lowest amount of decimal places, which would be the 3. But here I just wrote 12 too for the sake of time. So just if that clarifies anything. Okay? Alrighty. Okay, so now we're going to actually get into the real stoichiometry, and this is calculating limiting reactants, excess reactants, theoretical yield versus actual yield, these types of topics that were pretty much the meat and potatoes of your first exam, right? So if we're given a reaction, right, saying that we start with 86.3 grams of NO and 25.6 grams of hydrogen, and then you're asked to find the theoretical yield, radical, the limiting reactant, and then the excess reactant, right? And we're given the equation 2NO plus 5H2 will form 2NH3 plus 2H2O, okay? Okay, so before we jump into this, we need to understand what these things mean and what they are, right? What is theoretical, what is limiting reactant, and what is excess reactant? So essentially, theoretical just breaks down if this reaction completes 100% of the way, there's no waste, it's a perfect reaction, which doesn't happen in reality for the most part. How much can we expect to get a byproduct of? In this case, it's ammonia, right? It's the maximum amount. Like, there is no more possible because we've used 100% of the reactants. So that's theoretical. Actual is what it actually, like what it implies. How much did we actually yield? Usually in exams like the ACS or your professor's exam, the actual will be given to you. They'll say, in the laboratory, blah, 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 you produced this amount of X compound. That is given to you as your actual. You need to know that, right? And if they don't give you the actual, they might ask you to solve for the actual yield, but they'll give you the ratio of theoretical to actual yield, right? And so we got to jump into this. So limiting reactant is, again, reactant that limits the equation or limits the reaction, right? So it's just saying it's going to be the reactant that runs out first and stops the entire reaction from happening because it runs out. There's no more reactant to create the reaction. That's really redundant. So we have to calculate the moles of the product from each reactant. How much moles will they produce? So that's going to be our first step. So we start with what we have, right? So we're going to start with 86.3 grams of NO. And so we need to get that into moles of a product. Again, I'm just going to go with ammonia because it's straightforward, right? So to do that, we need to convert NO into moles first. So we're going to do 1 mole of NO is equal to its atomic mass, which I believe is 30 grams. N is 14, O is 16, 30. And so that unit conversion will convert us into moles of NO. Now we need to go from moles of NO into moles of a product. So we're going to have moles of NO on the bottom, 1 mole. Or oops. In this case, we have to use the mole ratio provided in the balanced equation given to us. So we know that 2 moles of NO will create 2 moles of NH3. So you can write it word for word, or you can just put 1 over 1. They're equal to the same thing. So we know 2 moles of NO will cancel to create 2 moles of NH3. And so now we just multiply that across, and that will calculate how much moles of NH3 ammonium we created, and I calculated that to be 2.88 moles of NH3. So that's the first part. So now we're going to keep that number, we're going to put it to the side, we're going to come back to it later. So now we have to start with the other reactant and see how much moles it produces. And the other reactant in this case is H2. And so we know we have 25.6 grams of H2. We're going to convert that into moles just like we did before. Over the 2 grams of H2. And then from there, once we have the unit conversion in moles, we have to cancel out and go into moles of the product, which would be 5 moles of H2, because to 2 moles of NH3. Oh, that's crooked. All right. And again, we're doing that because the balanced equation tells us 5 creates 2. So that's how we create the mole ratio. Okay? And so when you multiply that out, that will come out to 5.12 moles of NH3. So now we have to ask ourselves which one created more product. And so you compare the 2 answers you had. So you have 5.12 and then 2.88. So we know that the absolute most NH3 ammonium we can create is 2.88, the one with the smaller one, because that means that NO is going to run out, and so the reaction stops. So we're not going to go with the bigger one because there's more hydrogen than there is NO, so that reaction can't happen. So we have to go with the smaller one. And so we know that NO is our limiting reactant. So then as far as our excess reactant, it's the reactant that has excess or has been left over, which we know is H2. That's the excess reactant. So that's 2 parts of our question. And so now the theoretical yield is how much can we possibly make if it runs 100% of the way through. And we know that's going to be the same as our limiting reactant, because a reaction can't go past the limiting, because then you don't have enough reactants to create the reaction. So in this case, our theoretical yield will be 2.88 moles. And if it asks you for grams, you can just go back and convert that simply by taking the 2.88 moles of NH3, and then you multiply that, 1 mole, over 17 grams. And that will give you the grams of the theoretical yield. Any questions about that? Well, moving on. Okay. Okay, so the next part about solution stoichiometry, again, would be, sadly, is something you need to memorize that I can't really help you with. There's no really innate tricks or tips. It's just going home, putting in the hours, and just making sure you know all the rules, and that would be the solubility rules, right? So that's something that you guys need to do, right? And pretty much they're just rules that tell you, okay, these are the trends. If you put this with this, will it be soluble in water or not? I can tell you just usually ionics are always soluble. And so what's an ionic? It's a nonmetal with a metal. So if you see two elements that are on the opposite sides of the periodic table, one's a halogen or one's on the right side, or you have an alkali or an alkali earth metal, you can automatically assume that when they're put together, they will split back apart in a reaction. Okay? Then again, there's a whole table in your textbook that goes into more depth about all the specific exceptions and things like that. That's what you need to focus on, right? So going on from solubility rules, once you know that, you now can understand net ionic equations and how to break them apart. So here's pretty much my tip to you for net ionics, right? The net ionic will always just be the balanced equation of the two reactants that create the precipitate in the reaction, right? So if you look at an equation and you see that, oh, these two are soluble in water, but these two aren't, then the ones that are soluble in water will always be crossed out, and you're just going to be left with the two reactants that create a precipitate, right? So for example, let me pull up the solubility rules and I'll give you an example. Okay. So we have this idea that positive things like NH4 with any nonmetal are soluble. They don't have an exception. So if we say something along the lines of, let me make this Na SO4. Now, quick question to you guys. Is Na plus 1 or plus 2? Do you guys know the trend? Plus 1. Why do you know it's plus 1? Exactly. First group's plus 1, second group's plus 2. And then it works the same way on the other side, backwards, where fluorine, the halides are -1, then -2. Okay? So we know that that would be that plus, let's see, F2, right? So you know, because of double substitution, you just switch the front forward, and you're going to be left with NaF plus BaSO4. Now, we know, because of solubility rules, that Ba, when it's matched with SO4, it's insoluble. So this will be together. But Na and F and fluorine, or sodium and fluorine, they're ionic, non-metal metal, they will be soluble. So when you break it up for your full ionic reaction, it would look something like this, where you have Na2 plus SO4 2 negative plus Pa2 plus F2 minus. Right? And so for net ionics, you're looking at what changes. And so we can see that sodium stays the same, plus, plus. Same thing with fluorine. So you can cross them out. And so you're left with the net ionic reaction of SO4 2 negative plus A2 plus creates BaSO4. And this is what I mean when I say that for net ionic reactions, just use your solubility rules, find which reactants create the precipitant, and that will always be your net ionic reaction. So just for clarification, that this is the net ionic, while this crossed out one is just the ionic. Right? So they might ask you for net, which again is just the precipitate, or they might ask you for the full out ionic, which is just breaking everything into its own components, writing down its charges, and then following it along. Okay? So before we go full out, there's still some things that you still need to know about that idea, and that's oxidation states. So as far as oxidation states go, it's just the idea of whether you're gaining electrons or losing electrons. You're just looking at the charge within a reaction. So what we can say is that the trend is, by the acronym LEO, says GER, right? And this just stands for losing electrons, or in this case, becoming more positive. You are oxidizing, or it's oxidation. While GER is the same thing, gaining electrons, you are reducing, or being reduced. So remember that. That's an easy way to remember them. So now we just have to break up things into their ionics and then look at the charges and see if a compound is becoming more positive or more negative. Then we can use the acronym to identify if it's being oxidized or reduced. Right? So going back to that equation we did on this last one, right? Or does anyone still need the acronym, or are you guys all good? Okay. So going back to this net ionic, right? The reason we cancel out the sodium and the fluorine is because they're not doing anything. You can check by their oxidation states that they haven't moved ionically, right? Sodium has an oxidation, or an electron state, of +1 per 2, right? And same thing with fluorine, it's -1. But if we look here, because these bind together and become precipitate, they become neutral. And so that they've changed from -2 to neutral, +2 to neutral. So that's how it looks on ionic. But it looks a little differently when you actually look at different reactions independently. So let me see. Okay. Okay. So here, you have to go by explicitly what it tells you. So here, you would know that lithium is usually what? What's the charge on lithium? Yeah, +1. But in this case, it's neutral because it's not dictated to you otherwise. But if we assume it's +1, right? And then N2, what would N be? Not always. -3, you guys got to be very careful. Huh? Yeah. It's almost, it's not necessarily transitional like a transition metal, but in most cases it would just be neutral, right? Right, so 0. But in lithium here, we still have 6 lithium, so lithium has a charge of +1, while lithium times the 6 of them that are there, you have a +6 here. But nitrogen was just 0, so now it has to accommodate to that. It has to change its charge to accommodate and keep this Li3N neutral, because that's what it is. So if you have a +6 charge here, and there's 2 nitrogens, each nitrogen independently must become -3. Does that make sense? So this idea is you have to look them in relationship of the elements by themselves and then what charge they take place when they're inside of a compound. And that's how you can tell oxidation states. So in this case, nitrogen, which has gained electrons, what happened to nitrogen according to the acronym? Leo says GR. Exactly. Gaining electrons, becoming more negative, you've been reduced. So in this case, when it talks about agents, here's where you have to be careful because it can get very confusing very quickly. When you're talking about agents, you're talking about what caused the oxidation or what caused the reduction. So nitrogen has been reduced. It's gained electrons. But the reducing agent is lithium, because lithium is what caused nitrogen to become more negative because it stole, right, or it added, excuse me, backwards. It added, it gained electrons. So that's the idea of agents versus whether something is being strictly reduced or oxidizing. Okay, so we're going to call it a break. So if you guys need to use the bathroom, take a sip of water or anything, we're going to be back at 4:27. Yeah, that's 10 minutes. Okay. Need help or like?
Yeah, this is just this section. I just
Okay, so yeah, so the oxidation stuff is really just looking at the charges. Like, so again, you know,
that's what confuses me.
yeah. So the only times you assume something has a charge, like see how lithium is written as neutral. You know lithium.
How do you know if it's neutral?
Okay, so if we look at our periodic table, right? You know that all of these are neutral, like the transition metals. They transition states to accommodate for elements they combined with. And then you know that besides these ones here, these ones have their set charges just like these ones do. But anything else, nitrogen, like phosphorus, but so those ones are neutral as well. The only ones that are the exception are the ones on the ladder that you have colored here. So it's arsenic and this one that have the -3. So now that you know that, you know lithium has a +1. So it will always have +1. So you put +1 there. But nitrogen is neutral because it's in one of the groups that doesn't have a set established charged. And so you want to write +1 here and then a 0. But here they're combined. So when it's a combined, like a compound, that's when you have to look at whether it tells you a charge, because then it will tell you +1, +2, -1, -2. If there's nothing, you have to assume that when you add the charges of both of these together, it is 0.
Okay.
And so because of that, we know that lithium has 6 Nitrogen, which there's 2 of them, must become -3 then. It has to, because this is 0. And because it gained electrons, that's why it's being reduced.
Okay, so this would be -3.
Yes,
Right.
exactly.
Okay.
No problem. Oh, what's up, man?
Alright, so
Okay.
when it comes to this, right?
Yeah.
When they're all separated,
Yeah.
would it be acceptable to kind of switch them around to see if different combinations work?
Yeah, you can always play with it. I mean, you got to remember it's ACS, so it's going to be multiple choice. You can write it as long as you have your notes clear and you know what cancels out and what doesn't. The order doesn't matter, especially since it's multiple choice. The order will be put for you.
Yeah.
Yeah. But the actual order, like if you switch this Na like over here, as long as you know that Na is +1 on the left side of the equal and still positive on the right side.
No,
And-
but I mean like,
Okay.
because you see how like for example,
Yeah.
this is like this. So once they're all separated,
Yeah.
would we be able to kind of switch them around to see if different
Yeah.
compounds are created?
Exactly. And that's kind of what you do, right? So double elimination is when you separate like that, that's what you're doing. You're switching both, right? So this sodium will go with the fluorine, and then sulfate goes with the Ba, right?
Yeah.
And so the reason you do it double like that way is because you guarantee you've already tested all combinations. So you can do fluorine, you know negatives don't go with negatives, and you know positives don't go with positives. So by doing the double switch, you've already tested every combination.
Okay.
So you don't need to go through and test each one, because you'll know, like, as soon as you go to fluorine with sulfate, you'll realize, oh, they're both negative, they would never bond.
Right.
And that's why you can just switch the fronts,
Okay.
because that way you've tested everything.
Okay.
All right,
Thank you.
no problem. Oh, of course.
When you did question number 3,
Yeah.
I didn't get that answer.
Okay, what did you get? I may have had it different on my notes, so I did it really rushed. So if you did 3.71, or 3.7 times divided by 2. Yeah, I think I know what happened, because I did a different question, and so like what I've been doing is I've been rewriting the notes as I go, and I think I changed the question accidentally. So this is right. This is right.
Okay, perfect. Thank you.
Okay, when we reconjoin, I'll fix the notes. So what is it? It's 1.85?
Yeah.
Okay, let me fix that on my notes. Can you do me a big favor? Like when it's 5:20, can you let me know?
Sure.
Yeah, thank you. Yeah, that's the one I posted online. Yeah, it's on the it's not on the WordPress for the study union, but if you go to SARC WordPress, it is on there. That's an older view. It's like from 16. So if you scroll down, you should be able to find the answer. Yeah, yeah. So pretty much what I did is I based my so it should just be right here under SARC, Chem 2045 right there. And then it is right down. I think it's down here. Oh, what did I do?
I just had a little
Yeah.
corners.
It should be this, and then the key is right under it. Yeah. So,
Yeah, I just got all the
yeah.
functions.
So if you go back, like,
I'll download this one.
yeah, so that's the same one you have printed. If you press back, the link right under it is for the answers.
Oh, there's no answers.
Yeah,
yet.
yeah. So if you go back and then you go key right there. So what I did is this review I'm doing right now is very similar to that one. I just picked the questions I felt were most important. I changed the numbers a bit.
Okay, good.
Okay. Okay, guys, let's get started up again. Before we go back into where we were, I just want to point out in the notes, I made a quick calculation mistake. It's not 6.845, it's 1.85 moles on the balloon question with the ignition and stuff like that. That's my bad. I'm sorry, guys. So if you could fix your notes about that real quick, and then we'll jump right back in. No, they are. They're not on the Study Union WordPress. They're on the SARC WordPress. Yeah, so there's a review on the Study Union WordPress that has questions very similar to this, which I used as a basis to create this review. And then the answer key is on the SARC WordPress, and it's a link that says Haley Final Answer Key. So if you guys want even more practice questions, there's more resources for you. So, okay. So, good news, after you understand oxidation states and things like that, and solubility rules, you've done limiting reactants, excess reactants, that's it for solubility. We're moving on into gases now, right? And so essentially, let's work the formulas out real quick so we So there's really only a few main formulas you need to know for gas that are important, and I will save you some good time and effort because you do not really need to memorize all of the gas ones because of a neat trick, right? So the most iconic gas law, I hope you guys have it like seared in your brains at this point, is PV equals nRT, right? So there's a whole bunch of different formulas like Boyle's law and things like that that are manipulations and variations of this formula, like P1V1 equals P2V2 or things like that. And let me show you a trick that saves you some time so you don't have to memorize all of them. So again, going back off to the math of it, they're all formulas and derivatives of this formula. So meaning if we play with this formula, we can get all of the formulas. So essentially, let's say we want to know about two things. So we have a P1, a V1, a T1, and then again the same thing, P2, V2, T2. So instead of memorizing all the formulas, we can just play with this formula. So how you're going to do this trick is you're just going to take the ideal gas law, PV equals nRT, and you're going to solve for the variables that you're being asked for on one side. So ideally, P and V are already on one side together. We just need T, so we're going to divide it. So PV divided by T. And then once you have all of your variables on one side that you're looking at, throw away the other side. So instead of putting PV over T equals NR, we're just going to add ones here and say it's equal to itself, P2 V2 over T2. Does that make sense? You can play with the ideal gas law and get every formula you want. Just like Boyle's, you know that PV, they're already together. P1V1 equals P2V2. Or let's say we need volume and moles. You just get volumes, divide by moles, you have V over N, 1, 1, it's over. Does that make sense? Okay. So that way you really only need to know the ideal gas law because you can just manipulate to solve for whatever else you need. Sadly, ideal gas law isn't the only thing you need to know. You do also need to know partial pressure. And so that's this idea where partial pressure will always be equal to this weird looking X thing, which this just is the mole ratio multiplied by the total pressure. And so the mole ratio can be solved just by the moles of the part divided by total moles. So you just find the moles of the gas that you're looking for divided by the total moles of all the gases combined. That gives you your mole ratio. You multiply that by the total pressure in the system, and that will give you your partial pressure. Okay? And then finally, you can calculate density by just doing pressure plus divided by the gas constant, T. That's essentially what gases break down to. I would say these are the most important things you need to know about. And then remember that the gas constant R can be broken down into two forms, 0.08206 and 8.314. And remember the units. You know that you use 8.314 when dealing with energy, because the unit is joules per mole Kelvin. And if you're not dealing with energy, you're going to use the decimal, the 0.08206.
What's that right there? The D equals P plus.
Oh, yeah. This is just the pressure, and then this is just a reminder of the unit, like millimeters per mercury. How many millimeters of mercury are in 1 ATM? You guys know? 760, I heard it, right? Yeah. Also, important pressure conversions to know. I'll just squeeze it in here. 1 ATM is equal to 760 mmHg, or millimeters per mercury. That's also equal to 760 torr. Those are important things you should know because they might like to trick you up and say they'll give you the unit in this thing, and no, most of your formulas deal with ATM. Ideally, you want to be dealing with atmospheres. Also, another thing that you should know is, again, Celsius to Kelvin, Fahrenheit to Celsius. Just being able to format and play with that. You know Celsius to Kelvin, you just add 273.15. Then Fahrenheit to Celsius, you subtract 32 and multiply by 9/5 or 5 over 9. It's in your, I think it's 9/5. Yeah, so you take Fahrenheit minus 32 degrees and then multiply by 9 over 5. 5 over 9? Yeah. Again, textbook. See, like, I feel bad for you guys because when I took chemistry, I didn't have to memorize this. I was given a formula sheet. So even now, as a tutor, I still struggle with the formulas sometimes. But sadly, you have to adapt to your times. You guys need to know the formulas, so please know. Then add 32. Yeah. Yeah. Okay. So now that we got the gas stuff, let's actually do a problem with it. Anybody still need these notes, or are we good? Okay. Okay. So, oh my goodness. Okay, so lithium reacts with nitrogen and gas as depicted in the balanced reaction, right? Balanced reaction. And so you're given 6Li plus N2, 2Li3 nitrogen, right? And you want to find the mass of lithium that reacts with 58.5 milliliters at STP. Does anybody know what STP means? Exactly. And what are those units for STP? Yeah, it's 0 Celsius or 273.15 Kelvin. What's the pressure? 1 atm, exactly. So we already know that. We also know that our volume is at 0.0585 liters. We like things in liters, so that's why I converted it. Right? And so now we can work. So again, this is a gas question at first, but then the later parts are, again, just stoichiometry, converting back and trying to solve for what we know versus what we have. And so there's one thing we need to know, because we have a balanced equation, in order to solve for the mass of lithium, and that would be the moles of nitrogen. And good thing they've given us all the information about nitrogen as a gas, because now we can just use PV equals nRT, right? And we're trying to solve for moles, so some algebraic manipulation, and that will look like PV divided by RT equals N moles. And so now we can plug and chug. We know at standard temperature and pressure, we're at 1 atm for pressure. Our volume was given to us at 0.0585. And we divide that by the gas constant, 0.08206, times the standard temperature, which again is just 273.15. Actually, can someone double check for me? Because now I think it's 293. I think standard temperature might actually be 25 degrees Celsius. Is it 25? I'm pretty sure it's 25, but.
What was the question?
Standard STP, what is the temperature? It should be 25 degrees Celsius. I just want to, you know, it's 25. My bad, guys. It's 25, so it's not 273. It comes out to like 299 or 298 or something like that. I'll put it in the calculator, but I'm pretty sure it's 298. 25 plus 273.15. Yeah, it's 298. Yeah. Just know STP is 25 degrees Celsius. Okay? And so we adjust that, 98. And then we can multiply it through and solve for moles, right? And so we get 0.8206. We're going to get 24.46 divided by 0.0585. So you get 0.0024 moles nitrogen. in this case N2. And so now we just do the stoichiometry. We just say 0.0026 moles of N2 times the mole ratio going into lithium, 6 moles of lithium per, going back to our balanced equation, 6 moles of lithium are paired with 1 mole of nitrogen. And then we have to convert moles of lithium back into grams. And then and there is about 6.94 grams of lithium in 1 mole. Multiply that out, and we should get this is a 4, not a 6. You get 0.0996 grams, or in this case 99.6 milligrams. Okay. Let's.
0.08206.
Oh, that's R. That's a gas constant.
Oh, okay.
R.
Where did you get to 98.05 K?
That is the temperature at standard. 25 degrees Celsius. It must be in Kelvin, not Celsius. 25 plus 20.
It says the standard temperature here is equals 0 Celsius.
Yeah, so now I'm confused because I think your text says 25, but if you look it up on Google, it says 0, and that's why in my notes I had it as 0. But then I was like looking through the PowerPoint, and my PowerPoint says 25. So
I think
use 0 in class.
There's a difference that says there's standard conditions, which is 25.
Yeah.
And there's STP.
Okay, so STP, which was my original calculations, at 0. So that's a good clarification. Just to be sure, I would ask your professor to double check. But standard conditions is 25 degrees Celsius. STP is 0 degrees Celsius. So my original, in this case, it doesn't make that much of a difference because in my original calculations, I used 0 degrees Celsius as my temperature, and instead of 0.0024, you get 0.0026. So, and that just affects the answer in the long run, because instead of 99.6 grams, it converts into 108 milligrams. So it's a difference. So I would note it, but let me just write that on the notes here. STP 0 degrees Celsius. STC standard conditions equals 25 degrees Celsius. Okay? So at least we clarified that. All right, any other questions about this question? Okay. So that's that. Moving on. Okay. So now we're going to start introing into thermochemistry. And so we have this idea of, in thermochemistry, essentially some good conceptual questions that I can guarantee you they will ask you is exothermic versus endothermic and the perspective of the system versus surroundings. So be very keen on what perspective you're using, because if you have the wrong perspective, you are going to get the wrong answer. Right? So just to clarify, right? So if we have a beaker, right? Then we have ice, and it's sublimating. Can someone tell me what sublimating is? Yes, it's when you skip going into a liquid, you go straight into gas, right? And so we have this idea of water, which is often the negative Q, right? So you will have a bucket of water and you'll put boiling hot magnesium in there. And then you can calculate the resting temperature of the magnesium and the water. So always associate this negative Q usually with the water. That said, you won't be asked to remember specific heat except for one, and that's water. Does anybody know the specific heat of water? Exactly, we should all know that. So that's the only one you need to have memorized. So 4.18, everything else should be given to you. Okay. So that said, let us go into an actual problem. So we have a sample of 22 grams of water at 32 degrees Celsius absorbs 5.3 kilojoules of energy. What is the final temp? And so here we're given energy, again dictated by 5.3 kilojoules. So we know we're dealing with the formula that actually has a change in energy. Equals Q plus W. So is there any observable work done on this system? Do we have a change in volume or pressure? No, right? Usually you're going to see those in the type of questions where you have a non-rigid or an expandable container or surface, like a balloon or a rubber container, and they'll give you the pressure and then they'll tell you how much the container expands or contracts. And that's when you know work's done, and that's when you would use the W. So in this case, we can essentially just say delta E here is equal to Q, where 5.3 kilojoules is equal to the mass given, C, and then delta T, right? And so we can now solve for the change in temperature. And so we have 5.3 kilojoules equals 22 grams times our famous 4.18, and then our delta T. And so we have 5.3 or 5,300 joules divided by 22 times 4.18. And that will give you 596 Kelvin. So again, remember that is a delta T, right? So a delta T is essentially, I'm just going to write here, delta T is equal to the final temperature minus the initial. So now we know 596 is equal to the temperature final minus the 32, again, that's in Kelvin, so we have to convert Celsius into Kelvin here. 32 plus 273.15 minus the 305.15, and so you get 596 minus 305, and you'll be left with 291 degrees Kelvin is your final answer. Any questions on that? Oh, yeah, it should be added, sorry. Actually, yeah, it should be added. So in that case, it would be, good catch. No, that's still negative. It would be 11. It would be 901. Good catch. Oh, Sundays. Okay. Good? Oh, 901 Kelvin. 901. 596 plus 305 is 901. 901. Okay? Okay. Wow. Okay, so another question that's usually very important is Hess's law, or change in enthalpy, which is the questions where they give you a whole bunch of different reactions with their energies, and then they ask you to solve for like a hybrid reaction and how much energy that incurs. And so pretty much that's just, it's like a little puzzle. You got to play algebra with the equations and get it so they cancel out when you add all the equations out just into the equation you want. So I promise it sounds more complex than it actually is. So if we have carbon plus H2O creates CO plus H2, and that gives us 131.3 kilojoules. And then you have CO plus H2O creates CO2 plus H2. That will give us negative 42.2 kilojoules. And then you have CH4 plus H2O. That will give us 3H2 plus CO at 206.1 kilojoules. And what we're trying to solve for is how much energy does the reaction CH4 plus H2O, excuse me, it is actually 2C plus 2H2O creates CH4 plus CO2. That's the equation we're trying to solve for. How much energy does this one create? I'm just going to grab a new marker real quick. So essentially what we have to do for this problem is just manipulate the formulas so they'll give us that formula at the bottom, 2C plus 2H2O plus CH4 plus CO2. So I always like to start with getting the compounds to where they need to be, whether the right or the left, and then I worry about the numbers afterwards, right? So we have 2C plus 2H2O, CH4, CO2. So we know CO2 and CH4 must be on the right side. So we know CO2 is here. That's on the right side. There's no other CO2, but CH4 is here, which is on the wrong side. So what we can do is we can multiply this by a -1. And so that flips the reaction. But what you do to the reaction, you also have to do to the energy. So if we multiply this reaction by -1 to flip it, and then we have to multiply -1 by the energy. So now we have 3H2O plus CO gives us CH4 plus H2O at -206.1 Kelvin, or kilojoules, right? Honestly, these are both kind of dead, right? And so now we bring down everything else, right? CO plus H2O, CO2, plus H2. And then we have C plus H. Okay, so now we have CH4 and CO on the right side, but we need C and H2O on the left. So we have an H2O here, but we also have an H2O here, so these would cancel, right? Because when you add them, if they're on both sides, they cancel, right? So right now, technically, we only have one H2O on the left, which is not enough because we need two. But right now we're going to keep that problem on the side burner because right now we just want orientation. We just want the compounds where they need to be. So the next thing we need is C on the left side. So we look, there's no C's on the right side, and there's one C on the left side. Okay. So now we have our products and reactants where they need to go. Now we need to get rid of everything else that doesn't belong there and get the coefficients on the compounds correct. And so how we do that is just like you saw with the H2O, we get them to cancel, right? So we have a CO here and a CO here. So we know these cancel. Is there any other CO? So since we can't find any other CO on the opposite sides, we see that we would still be left with a CO when we add them up. So how we have to do this is we have to put a coefficient on the multiplier so that we can get it even, right? So what we can do is we can multiply this side by 2, right? And so this would result in us having 2 COs, so we can cancel both of them out. Does that make sense? It's like a puzzle. We're trying to get all the pieces to align. So, and also, if you notice that when we multiply this one by 2, we also get 2C, which is what we need here, 2C. What's up?
Did you mean to put 3H2O or just 3H2?
It should be 3H2O. Because when we multiply this one by -1, it flips it. So it is H2. Good catch. Yeah. It's H2. Okay. So now we should have 3H2 plus CO, CH4 plus H2O, that's 6.1. Okay, and so now we're going to play the cross-out game again now. So now we have 2C, no C's on this side, so 2C will stay. We have 2H2O, 3H2O, so 3, and we see that this H2O will cancel this H2O, leaving us with our 2C and our 2H2O. Then we have this 2CO will cancel these 2 COs. And then you have this 3H. We need CH2O, 2C. Wait, hold on. Did I copy it right? Oh, this should be 4, excuse me. So now we cancel 2 COs and we're left with 2 CO here. And then we want H2. So we have this H2O cancels one of these H2Os, and then we have two H2s here. Again, this, yeah. And so pretty much, so yeah, and then these two H2s will cancel these two H2s, which leaves us with a problem now, because now we don't have H2 in our answer anymore, and we need it because we are trying, no we don't, excuse me, I'm sorry, I'm getting this, it gets messy. So the H2s cancel, and so we are just left with 2C plus 2H2O plus CH4 plus CO2. So when you add it all down, you can say 2C plus 2H2O is left CH4 plus CO2 okay, plus 2C, yeah. Okay, so we still have a problem here. So we're almost done, but not quite left, because now we have everything where we need it, but we're still left with 2CO at the end that we need to get rid of. So we have what we're looking for, 2C plus 2H2O, CH4 plus CO2. So what we can do here is, we look, if we multiply. Actually, no, we're good, because these cancel, because the original formula is just CO, so when we multiplied it by 2, like here, we'd only have 2CO. So this 2CO cancels these two out, and CO is done. I don't know what to put for, that was my bad. So yeah, it can get very messy, as you can see, so my offer to you guys is really just focus and be very thorough with what you're writing. Like, make sure you double check your equations, because if you do like me and you mess up, you'll see that it gets really confusing because you'll write the equations wrong and then you'll start heading in the wrong path. But if you take your time and you just keep writing each equation, double check that you wrote the equations right when you rewrote them, it's really not that hard. You just use negatives to flip it, or coefficients if you need more of a compound to cross out. And so now that we got the equation what we wanted, and we already manipulated the numbers, we just add the numbers up. So originally our numbers were 131.3, negative 42.2, and 206.1. We did negative 1 to the 206.1, so we're left with negative 206.1, and then we multiplied by 2 on the 131.3, so we're left with 262.6, and we never touched the negative 42, so we just add them together. So you get negative 248.1 plus 262.6, and so you subtract them, you will get 7. I did the subtraction wrong. This is why we have calculators. And so you get negative 14.5 kilojoules. Okay? I know it's a lot. It was even a lot for me. Like, wow. Doesn't instill the most confident when your tutor's messing up. I promise you guys it's not that bad if you just take your time and you just make sure you write the equations right, because that's what gave me troubles. I was writing the equations wrong. Okay? Okay, so let us try to burn through this last part. Here's the good news, the math is over. The math is over, that's it. That's all the math in Chem 1. Now the rest is very, okay, that was a little bit of a lie because there's just some math, but it's like very simple addition. If you can't, it's just adding, like counting, okay? Because the next is just quantum numbers, and then just the Lewis structures, and then the trends. So we're going to kind of burn through these a lot faster, because these are just things you need to know, and just trends from the textbook, okay, right? So quantum numbers, you have n, which is your principal quantum number, L, which is the angular quantum number, and M, as in Mary, is the magnetic quantum number. So there's these three rules. Oh, it's always crooked. These three rules that you need to know when selecting quantum numbers. One is n can be any integer except 0. It cannot be 0 and it cannot be negative, right? So n can really be anything except 0 or negative. That's all you have to worry about, okay? Next is L is any number from 0 to n minus 1, which means that if n is 3, L can be 0 to 2. Or if n is 7, L can be 0 to 6. Does that make sense? L will always be in a range between 0 and 1 less than your selected n, or principal quantum number. And then M is negative L to positive L. So if L is 3, M can be negative 3, negative 2, negative 1, 0, 1, 2, 3. Anywhere in that spectrum, right? And then you have a small note on S, which is at the bottom, which refers to spin. And spin is really just this idea where it can be positive 1/2 or negative 1/2, which just dictates the rotation the electrons are spinning. And that's really only to test your knowledge on Pauli exclusion principle, which just means that every set of quantum numbers is exclusive and cannot be rearranged. So if I give you the quantum numbers of n is 2, L is 1, M is negative 1, and then I copy that twice, one of them has to have a spin of positive 1/2, and the other one has to have the negative 1/2. Otherwise, they cannot exist. That's all the S is. So usually you only see it when it's trying to test Pauli exclusion, and you're just looking for the numbers that have the same in everything except the S, because those are the correct numbers. Okay, does that make sense? So again, this principle is actually really easy to test. All they'll do is they'll list off numbers. They'll be like, n is 3, L is 4, A or M is 2 or something. And you would need to know, oh, 4 is bigger than 3, L can't be bigger than n, so those numbers are wrong, false. That's not a true set of exclusion or of quantum numbers. It's really not too complex as long as you remember those three rules. Then also something else to associate with is they might ask you about the orbitals, and that's dictated by the angular number, which is L. So if L is 0, it goes in order. So you know it goes S, P, D, F. So if L is 0, S, L is 1, P, 2, D, and 3, F, right? That's it. That's pretty much quantum number. Yeah, okay. So I'm going to keep trying to burn through this because I at least want to get through this entire thing. But there's 10 minutes left, so if you guys could fill out the surveys that are in front of you while you listen to me, and if you guys have any like last-minute out-the-door questions you want to ask, just write them down, and I'll try to get the last 5 minutes for you guys to ask those questions out. So while you guys do that, the next thing is electron configuration, which again is periodic trends and just knowing your periodic table, knowing that the first two rows are 1s, 2s, like S1 and S2. The middle is the transition middle, or metals, which have the D, D1, D2, D3, all the way up to D10. And then the next two, where the nonmetals, are your P, right? And then your two bottom rows at the very bottom of the periodic table, those ones have Fs. And so essentially you just go in order. You just count the amount of electrons. So oxygen, for example, has, according to the periodic table, has 16, right? Is that just the atomic mass and I'm getting it wrong? I will pull up the periodic table real quick. How many electrons oxygen has? It's 8. It's 8, right? Oxygen has 8 electrons. So if we know oxygen has 8 electrons, you just count, right? 1s, 2, 2s2, 2p. If that's 4, this would be 4, right? And then the valence electrons on the electron configuration are the electrons on the highest number. So in oxygen, the highest number is level 2, so you count all of them. 2 plus 4, that's 6 valence electrons. That's how you do it. And again, there's the shortcut using your periodic table, where you can just look at what row or what column it is, and it should tell you, like, okay, this is in the P row, so I know it should end in P4 or P3, and so on, right? These are some important trends to know on the periodic table. Ionization energy is the energy required to remove an electron. So as you get more and more electronegative, which is in the direction pointing in fluorine, or this arrow here, your ionization energy increases because it becomes more electronegative, and so the compound or the element wants to keep its electrons very badly. So it's going to fight pulling them off harder. Electron affinity goes in the same direction because it's a measure of how easy it is to add an electron. So if it's really hard to pull off an electron, you're going to assume it's really easy to push on an electron, and that's why they're in the same direction. Then atomic radii goes in the opposite direction of electron affinity and ionization energy, because the further down you go on the periodic table, the more energy levels there are, so the radius is bigger. But if you move to the right, there's more protons, so there's more electronic pull, so it pulls it in closer. So that's why it's down and to the left is for bigger radius. Then hybridization is all about, is there a double bond, is there a triple bond, or if there's single bond or lone electron pairs. If you have 4 distinct areas of electron density, be it 3 single bonds and 1 lone electron pair, that's sp3. But if there's 3 distinct areas, like a double bond and then 2 single bonds, then that's sp2. If there's 2, like 2 double bonds, that's just sp at that point. And then 2 or less goes to s, right? So that's hybridization. That's how you can count. So you just look up, is there double bonds or is there triple bonds? Because that will determine if you're sp3, sp2, or sp. Okay? Yeah, that's about that. And then, again, Lewis structures. I'm just going to go ahead and do carbon, right? So you know carbon, you count the valence electrons, you add them up together, and that's how much electrons you have to work with. So in this case, carbon is the least electronegative, so it goes in the center, while fluorine surrounds it. And you got to remember that the octet rule must be satisfied. And the octet rule just says that every element within the Lewis structure has 8 electrons surrounding it, whether it be shared or isolated. So bonds count as 2. So 2, 4, 6, 8. So carbon is good. But we still need fluorine. Fluorine only has 2 surrounding it because the bonds are shared. So those 2 count towards fluorine as well. So we're going to add another 6. 1, 2, 3, 4, 5, 6. And you do that for all of it. And that would be the Lewis structure for that. Now, where it gets a little complicated is when you're given compounds that don't have enough valence electrons, so it can just all be single bonds and then lone electron pairs, right? Sometimes you're not going to have enough electrons, so what you have to do is you have to share even more. So let's say this isn't the case. This is the correct answer for CF4. But let's say there wasn't enough electrons. That's when you have to share. You get rid of a lone pair and add it on to the double bond. That's when you see double bonds. So you add up the valence electrons. You assume there is enough to do single bonds and then lone electron pairs. You count how many electrons that drawing has. And if you don't have enough, that's when you go to double bonds. Okay? So that, and then again, this last question is just testing the trend, knowing which one's the larger atom. You're just going off of the atomic mass, right? Which one's bigger? Or if it asked about radii, you would go off of the trend. Okay? Any last minute questions that you guys want to personally ask me? Okay, no? Or you got something? Okay, guys, again, 2 hours is only so much we can work with, but there are other chemistry tutors. Laura has a session too, so if you want to make her, I'm sure she's going to cover things I didn't. But this is the best thing. I hope I at least showed you guys some areas you need to work on more and some areas that you know you're confident in. And by no means is this a conclusive thing, because again, I can't get through a whole semester at 2 hours. So please do keep studying. Good luck on your finals, guys. You're going to do great. And remember, for the chart, if anybody wants to take last second, these are things that I didn't cover in depth, but I think are really essential to the final. Okay? Huh? Yeah. So I'm just going to come around and collect the reviews if you guys have those done. If you don't, just finish it and then leave it on the table, and I'll collect it afterwards. Okay? Thank you for your time, guys. 34.